Our meeting recording has been started. Thank you.
Yeah. Good afternoon, everyone. And thank you for this wonderful opportunity to present my work in this Hyperledger community forum. Yeah. So I'm basically working National Informatics Center, Govt of India. Almost for the past 27 years, 27, 28 years, I have been working there. Started with the scientific assistant as a career, and then I step on to become a senior person there right now. So mostly I work with networking. So I am one of the, I'm taking care of the Tamil Nadu region for National Knowledge Network, which is being implemented by our organization. And very recently, I started my academic pursuit. Again, I think in 2017, I just joined the postgraduate program in one of the universities called, Bharat BSc, BSc Crescent Institute of Science and Technology. Now it should not be called as deemed university, should not be called as university. So it is named as BSc Crescent Institute of Science and Technology. Some of you from this region may know that the Crescent Engineering College. So where I enrolled there as a flexible mode of doing my MTech program. And this is my final year, the final semester project work, which I did. The title is Trustable Logs Using Blockchain. So I didn't put my organization logo. I just put a college logo because the project's carried out in the college. So I put it in my presentation, the college logo. Fine. So the title is Trustable Logs Using Blockchain. So what is the Trustable Logs? So this idea of the preserving the logs has been in my mind for a very long time. So I used to encounter a lot of, the regulators and all where they ask for logs. And every time I present a log, I used to think myself, what happens when the administrator changes the log and then present it to the regulator or auditor? So what happens with that? How the people can really trust my log? That's a question. So the events are, I start with the presentation. All the events are recorded as logs. For example, if I write a mail to someone, so there will be some log somewhere else. The mail server will record that from address and to address, what is the size, timestamp, everything is recorded. So when I change a route in a router, then that can be recorded. When the internet is exchanging BGP routes, that can be logged. So we'll come about, some of the use cases where it will be more useful, I'll come later. But any events can be recorded, that is called logs. It can be used for debugging purposes, capacity planning, accounting, etc. As I told, regulatory authorities requires these kind of logs. And most of the legacy log systems are tamperable, which means that when I'm giving, when somebody asks me my log, my server log, I can always tamper it and then give it to him. There is no way he can really check it up, whether it is there. So it happens everywhere, and this is somewhat a difficult question to answer. So whether my logs are tampered or not tampered. Even in the courts, they will be asking, how do you know that that particular log is not tampered by that particular administrator? What are the investigations you have done out of band to know that these particular logs are not tampered? All these questions are natural, and it is there in the system. So the warm devices can address certain issue. This issue. See, what happens is I can write once and read many times devices, some kind of an optical device where I can keep write it. So I can't tamper it very easily unless I have a very sophisticated machine. So I can use a warm device, but it is a very costly. It is not economically feasible in most of the solution. So the solution is whether can I use blockchain, because blockchain means back of the mind, it always reminds me, yeah, there is some immutability factor in that. Can I use blockchain for for making the logs tamperable, or if it is tampered, at least I can know that, yeah, this particular set of logs are tampered. This particular set of logs are not tampered. Some kind of the mathematical proof it can give. Can I use blockchain for that one? So my whole thing, investigation and implementation on this particular part of it. So the work we carried out has got two phases, phase 1 and phase 2. And phase 1 is basically the study. it was carried out in the last semester, August 2019 to February 2020. So I studied some of the things, some papers, literature survey, what other things are there, thinking about that part. And most of the time I spent on Rust language in that part. So I wanted to implement using Rust language. The reason is this is an opportunity that I can learn a new language, practice a new language. And so unless there is some kind of a pressure or some kind of a push within myself, I'm not going to do anything on that part. So this is a natural scenario where I can take the opportunity to self-push to learn a new language and learn a new technology. That's the thing. So the phase 2 is where I really put a code and then make it, done a code and then implemented that part. So this work, I got two styles of blockchain implementation, style 1 and style 2. What is that style 1 and style 2? So any blockchain, for example, if I want to learn blockchain, if I hear the word blockchain, back of the mind, I always refer to Bitcoin. So I started reading the Bitcoin and that style, the Bitcoin style, whatever the transactions happening, it is just stored in the blockchain itself. So whenever I want to retrieve something, I retrieve from the blockchain. It is some kind of a log. It is some kind of the glorified log. Bitcoin system is some kind of glorified log where everything I put as a transaction and read the transaction one by one, so that I put a bit sigma from transaction 0 to transaction n to arrive exactly what is the status of the whole thing at transaction n. So that kind of style. Then comes the Ethereum style, where they put a state, where they put you got something called a state where you can store a state, and whatever the transaction can be stored as in a state, and whenever you want to retrieve something, you can retrieve from the state. The good example in that Ethereum, the white paper and yellow paper they quoted is the bank example. Suppose I want to transfer, Alice want to transfer $5 to Bob. So basically you can implement the conventional banking system, the same thing you can try to implement as a state in the blockchain. So that is the style 2. Why initially I started working with style 1 and I almost finished the project. Then I started looking at the videos of Dan Middleton. So in one point he told that people don't use state is not at all a blockchain. Then it is a whole nightmare. Oh, this person told it is not a blockchain, so whatever I implement, it's not a blockchain. Then again I started from not from a scratch, but from the middle, from laterally I started, and then started implementing as a as a state, as a full state. I'll come about that one, what are the structures I used and all. So the platform I've chosen is the Hyperledger Sawtooth platform. This I decided last year itself, because one of the reasons is that it supports Rust SDK. So I want to do with Rust. I want to learn a new language. So I started with that part. The consensus algorithm is PBFT, and programming language I use is Rust. Implementation, it is a 4-node blockchain cluster in AWS. For each style, each set of styles, I use separate four nodes and 4 nodes, and plus few nodes for handling the client part and all. So the style 1 is basically a single state. I just use only one state. I think 0 ending with 01 or 00. I don't remember right now, but only a one state. I started putting the transaction in everything in that particular state. Only thing is, when I want to retrieve, when I want to do some verification, I started digging the blockchain for the transactions and do the computation. The style 1 is the multiple states. There is no transaction digging. And I know that my logs, the particular part of the log, which state it is stored, that is a very simple, straightforward, that the transfer function is written so that I can retrieve the particular state of that part and use it for my verification. The next one is, it is a off-chaining. The logs are taken as a file block. You know that, coming back, what is a log, how the logs are stored. Logs can be, I'm traditionally a Unix person. So the logs are, the syslog is the only thing which comes to my mind, where I can configure the syslog and I can store the stream of the event logging at various files continuously, and mostly it is a text-based files. And there are logs which are binary file also. So what I do is, suppose I take one particular log, it is a stream of bytes stored in a file. What I do is, I can store the entire thing in a blockchain, but it is not practically feasible because of the size. What I can do is I can take the file blocks. I call it as a file blocks, 0th byte to so say some n number of bytes. I'll take that part, take a hash of it, and then the hash represents that particular block. Anything is stamped in that particular file block, it will be reflected in the hash. So basically, I take the hash and then I store the hash in the blockchain, not the real block file, the log file. The size I have taken is approximately 1 MB and use SHA-256 for that one. And in this way, I can establish what is called the partial trust establishment. Suppose somebody is presenting, I am an auditor, somebody is presenting me a log file, say about some 400 MB, something like that. The tampering could have been happened at some particular place, probably at the end of the log or the middle of the log, somewhere else. So if I know that some tampering has happened there, I need not throw the whole log. I say that I can't trust that one. I can take the hash I can divide the logs into multiple blocks, take hash of each block, and the hashes which matches, that I can always trust it. The hashes which don't trust, I need not trust that. I can just throw away that particular thing. So the partial trust establishment we can make if I do the half chaining, and if I take the file blocks of fixed size, and then I can do this part. It need not be fixed size, it can be a variable size also, but we can do this part. So these are the papers I did. Basically, I'm not a very savvy on literature survey and all, because this is for my academic requirements. I need to go through this one, but the good papers have come, so I referred these papers. So the one particular paper which is this thing is the third one, the Castro and Liskov. I think it is written somewhere in 2000 or 1997. I don't remember that particular date, but it's a very difficult paper for me to read, and I have not done the complete reading of that particular thing. Partly I've done that one. And the next paper is the Vitalik Buterin. It's a wonderful paper. It's a beautiful paper. I think every blockchain person should read that paper. Next generation smart contracts and decentralized application platform. Wonderful paper. That white paper is. And this one is another wonderful paper. Logan Seeley, Introduction to Sawtooth PBFT. In fact, I learned PBFT from this paper rather than the Castro and Liskov paper. But since I have gone through that paper to some extent, took printouts and put some reading, I put it over here. In fact, sometimes I regret why I put over here, but that's the reason I just put it. So a lot of online sites, videos, Hyperledger and Rust forums, emails, tons of mails I received from Rust forums and Hyperledger, especially from Mr. Arun. So this is my system architecture. So these are the blockchain nodes. I have 4 blockchain nodes I have over here, and these are the log sources. These are the log sources. What happens is, in this one, I'm not generating the blockchain in real time. I want to make it as an off real time. Say periodically I run. I'll just explain what is that part. So these are the blockchain nodes, and this is a reliable. It is a syslog network. RELP is a reliable the log transfer network, something like that. This is a RELP network. We can configure with R syslog-D. You can really configure. But in real case, it need not be using the syslog-D RELP. It can be even Apache Kafka or any other log transfer mechanism. You can use that part. The log sources generate logs. So whenever there is an event, whenever the router communicates, makes a BGP update to the neighbor router in the internet, it can generate a log. So these are the log sources. I'm taking, for this particular example, I'm taking only one log source. So the one log source is generating the log. Whenever it generates a log, it spits over here. Immediately the log reaches all these places. Nothing will happen. Only the log gets stored. The reason why I'm immediately sending is, suppose if the log is generated at 9 o'clock today, at 9:30, someone is arm twisting me and then asking me change the log and then send it. Then there is no, I need to do that part. Probably I may be doing that part, and then the logs will be transferred. Suppose I'm sending this log in real time to all these nodes, then the chances that assume that these are all having an independent authority. For example, this could be say an intelligence bureau, this could be NTRO, this could be my neighbor, my cousin organization, this my sister organization. So the obvious thing cannot be possible at each and every place. So that's the thing. In real time, I'm sending the log, but I'm not generating the blockchain in real time. I have some reasons for this, some technical reasons for that. Basically, I don't say a technical reason. Some constraints I had initially. So that's the reason I'm not generating. We'll discuss about later that part. So in real time, I'm sending logs to all the nodes. At the end of the day, say for example, 6:30 p.m. or 7 o'clock, 7 p.m., then I started running from my client. This is my blockchain client, one of the client where I fire the transaction, where I also get have the copy of the log. I'm representing this one. Then I just fire I create a transaction and then fire a transaction over here, and then the transaction processor running over in all the blockchain nodes creates the blocks, and then the blocks are very available. So later at some point of time, say after 6 months or 1 year, then the auditor comes and asks me for some logs, or some investigation agency comes and asks me a log. So I'm presenting him a log with a file, but he can't trust my log file, but he can trust always the blockchain nodes. Then he queries the blockchain and take the states or do a transaction digging, whatever way he likes it. Then he compares the hash of my logs and this particular log. For example, the transaction says that the first, I'll come about, what is the transaction structure and all. The transaction can say 0th byte to 100th byte, this is the hash. So then from the log, he calculate hash for 0th byte to 100th byte and check the hash with the blockchain hash. If it is true, that's fine. The auditor can query any of the blockchain nodes so that he can satisfy himself. You can query the whole thing also. He can query and then satisfies, and moment he satisfies, then he can analyze that particular log for that particular investigation or whatever it is, then he can go forward. So this is the whole setup I have done. So this is what I have, the same thing is written. Logs to be delivered to all blockchain, preferably in real time. It's almost real time. Transport I'm making with rsyslogd, that is RELP, Reliable Event Log Protocol, which is part of rsyslogd. Transactions are generated by clients associated with log source. They send to blockchain network at fixed time, maybe periodically. Each transaction represents a fixed size file blocks in the log. The transaction payload comprises of file block boundaries and its hash. Partial trust establishment, as I told. And after block generation and its addition to blockchain, the logs in the blockchain can be removed. So what happens is once the blockchain is removed, so I need not store the 400 MB or 4 gig or whatever the log file over here, that I can always remove that part. So that I can use that space for the next day creation of the blockchain. So what are the software modules I have? I have a client module, the transaction processor module, and verification module. Client module on behalf of log source takes the log stream, create transaction batches, send it to the Sawtooth validator or Sawtooth nodes. The transaction processor is a business logic. It runs in every node, and it does the semantic validations of transactions. In my case, the semantic validation is hashes in the transaction. So for example, when the client sends a transaction, whether that hash and what hash it has to be, the transaction processor can determine. If it is correct, then it approves it. The PBFT ensures that committed blocks are all valid, and the verification log is what the auditor is doing that part. So this is the structure I have. The basic payload I have. So I should have some kind of an ID for representing what is the log source. So there are two styles I told, style 1 and style 2. Style 1 I started with a very short the vision that I use only U32 as a start byte, but that is not sufficient. So in style 2 I use that U64. What is the start byte, what is the end byte, and what is the hash between that part. So this is a very simple payload, and I use CBAR for completely serializing that part. Why I use CBAR? Basically, it is from IETF. I am inclined towards IETF because I'm a network guy. And it is a very good, on learning about CBAR, it is a very good and beautiful the serialization one can do with CBAR. I really like that. So this is in the overall the structure. I mean, I read the blocks. Yeah, I read the block, file block, generate payload, push it to some kind of a list, and then if the list is over, I mean, normally in Sawtooth, what happens is the transactions has to be batched, and then the batch has to be submitted to the validator. So I push it to the some kind of a list, the payload list, and when the count reaches say 100, then 100 or 101, I just give it to the batch generation, and then I send it to the validator. So this is how the transactions and the batches are generated. So I have a payload, and I can have some kind of an the representation, the serialized representation of that. It could be CBAR or protobuf or even CSV, simple CSV. I have some kind of keys, the crypto ECC keys I generated and have. So I use those keys for generation of the transaction header. Then I create the transaction, the complete transaction I created, transaction header plus the payload. Then I push it to the batch header. Then I do the batch header because I want to put, I want to do the batching. Then I send it for batching, and I generate the batch header. Then finally, after the batch is over, I give it for submission to the validator. So this is very difficult. This is the whole thing. I just put it how exactly it is all happening, the whole thing. So it comes very well in the document, but it is not in the PowerPoint. I skipped this particular slide. So the same thing, the transaction IDs, each batch, then how I'm generating the batch from the transaction list. I take the transaction, I put it in a batch and generate the batch header and the serialized, and finally the batch list is serialized, and then it's sent to the validator. So in Sawtooth, you've got three parts: the client part, the transaction, then you've got something called the validator part. Then in the right hand side, you've got what is called the transaction processor module. That is your application. So basically in any Sawtooth application, you will be writing the client part and you will be writing the transaction processor module. The transaction processor module resides in the validator. So it runs in every validator. It should run in the every validator. And whether an application should have only a one single transaction processor or multiple, it can have a multiple transaction processor, can run at the same time. You can do load balancing, and for performance reasons, you can use that part. So in my case, I'm using only one transaction processor module. And there are get and sets method, which transaction processor module, and which can communicate with the back to the validator. So the node contains, again I'm coming, the node contains validator part and the transaction processor module. So the application is, your blockchain, Sawtooth blockchain application is, it is a client part and a transaction processor module. As I told, it is going to reside in the validator. Validator calls apply method of the transaction processor, which it implements. And I'll come to this part also. This is the one. You've got validator and transaction processor. All these things are going to reside in the node. So the registration happens, and get and set, it can use that part. So this is the registration. So this is a transaction processor, how it is looks like that. This is a validate. Everything is there in the same box, in the same node. So you got a validator. I got a transaction processor. So this is basically a struct in Rust SDK. So I implement, I create another struct called my handler, for example. So I'm using this transaction process struct inside that part. And I got these function name, family name, versions, and namespaces. So in Sawtooth, what happens, every application should have, the family name is basically an application name. So the application name is the family name. It can have various versions. So that is the very reasons you got versions. And namespaces. The namespaces, I think next week or so, Arun is going to take about the entire, the trie structure, the Merkle tree, the Merkle trie. So there we can understand what exactly the namespaces are. The namespaces are, this namespaces is very, the entire structure, the entire trie, the radix trie, is common for the whole Sawtooth application. There can be multiple applications. It is something like, you got a lot of, you take any computer, for example, in Unix machine. Unix runs a lot of processes in that one, but there is an address space for each and everything. For example, the processor for my transaction processor can run in an Ubuntu Linux. It can cause address space. My own cal function can run in a separate address space. My own other function can run in my Rust compiler can run in a separate. Each is having their own address space in the global memory. So the entire Merkle radix trie is a global space where many applications can have. And in that, I'm sharing some of the spaces for my application. That is a namespace. So I implement a method called the apply is one of the functions which I need to implement, because what happens is whenever the validator gets a transaction and if its syntax are okay, then it calls the particular apply method matching the family name version, and then that particular apply method is called. That is how the validator knows which apply method to call depending upon the transaction. The transaction header carries these things: family name, family versions, and all. So the match is made, and then accordingly it is made. An address space, I'm sorry, namespace. The matching is done, and corresponding appropriate transaction process apply method is called. While calling, it passes what is called TP request, a struct and a trait object with full of lot of parameters. Then the entire transaction, I can get it over here, and I can use get and set method for setting. For example, if I'm happy with, if my business logic is okay, I can set that particular thing. Setting means, yes, this particular state I can set as this part. That is the thing. This I can do this part. So this is how it can be carried out. Then the verification module. So what happens after the transaction, after the see this runs on in my 4-node network. So this TP is running in all the nodes. So in the PBFT node, what exactly happens is I can tolerate 3f plus 1. And the 3f plus 1 equal to n. Suppose if I have n number of nodes, I can tolerate the one node failure. It could be a Byzantine failure. So one node failure, the system can tolerate. So all the nodes, they're running the same, the transaction processor. They come into consensus PBFT. They generate the block. PBFT root hash is get shared, and then the blocks are created, consensus is reached, and blocks are pushed to the blockchain. So the blocks are generated for this thing when the transaction rises. Normally, a block is generated for every batch. Verification, the module. The log source presents the log stream module. For example, some auditor comes. So here he comes to me. Then I'll be presenting my logs. I give him a file. Sir, this is the file. You have it. You can verify it. The auditor runs the verification program, compares the hash of submitted file blocks with the payload data in the blockchain. First, he take the hash of my thing. And for example, I'm sorry. The first he can query the blockchain and take the transaction, and from the transaction he can take the payload. From the payload he can determine what is the start byte and what is the end byte and what is its hash for that particular block. He can do the computation of the same thing in my submitted file block. If they are matched or okay, that block is okay. He keeps on doing till the end of the log file. In my style 1, it's something like a Bitcoin. I have to dig the transaction and from the blockchain. In my style 2 verification, I just takes the payload in the states. I just query the state and then take it out. And REST API for extracting the blocks or states from the blockchain. The verification program will use REST API and queries the validator. So these are all the screenshot. So I have ready. I just show a small demo. It is ready. I'll just show a demo right now. Just takes not more than 5 minutes, I guess. So